So I'm hoping that you guys are pretty good at shifting graphs. The one thing that people screw up a lot is, say, right here or here, they forget to put in the square or the cube, etc. But another thing that gets easily mixed up is when you're shifting to the right and you have something that faces down, that negative doesn't change what's inside. X minus 6 is still going to shift to the right, and then the minus 3 is still going to be a vertical shift down. That negative only affects the way that this opens, so it's going to open down. Speaking of open down, you should recognize that this is going to be an even degree polynomial that has to open down. So what does that mean for the equation? Eventually it means that there's going to be a negative there. If you look at the roots, you get their binomials, you get their behaviors, and from their behaviors you get the multiplicities. From the multiplicity you get the degree. This should be a degree 6 polynomial, which matches the idea that this is an even degree polynomial that faces down. There's your product. Problem number 3, that's just another example of the end behavior of polynomials. In this case, you've got an odd degree polynomial with a negative leading coefficient. So as you move to the right, it's going to go down. As you move to the left, it's going to go up towards positive infinity. Yay. Let's keep going. The graph of the inverse. Personally, the way I get the graph of the inverse is I start by interchanging some coordinates. So instead of 0, 2, I've got 2 and 0. Instead of 3 and 5, I've got 5 and 3, and then likewise 8 and 4. That also helps me out when I'm chasing after the domain. The domain of the function, and I hope you caught this, that's a hollow dot there at x equals 0. So it means the domain doesn't include 0. So I goes from 0 to 4. 4 is included. 4 is included, 0 is not. Over here, for the range, 2 is not included, but 8 is. Now, when you move from the function to its inverse, something nice happens between the domain and the range. What is it? They interchange. Good. So this becomes 2 to 8, and this becomes 0 to 4. Done. F inverse of 5 is going to be 3. There's your inverse function. Y equals F inverse of x. Problem number 6, the part that you guys need to remember, there's actually 2 tricks involved in this. Once you switch x and y, you're going to multiply both sides by the lowest common denominator. That's 3y minus 7. That'll cancel from the right-hand side, but not on the left-hand side. If you distribute that x term to both terms inside, you get something that looks like this. My eventual goal is to solve for y. So what I'll do is I'll move the 7x to the right-hand side and the y to the left-hand side. What happens to a term when it changes sides? Changes signs as well. So negative 7x becomes a positive 7x. Positive y becomes a negative y on the left-hand side. Factor out the y from both of those terms. If you do that, then you can divide both sides by 3x minus 1. On the left-hand side, it cancels. On the right-hand side, you get the expression for your inverse. Don't forget that last little point for writing f negative 1 of x. Problem 7. This one's a lot of work. First thing you can look at is the list of possible rational real roots. And there's a lot of possibilities. Remember, p comes from the factors of the last term. Q comes from the factors of the first term. If you looked at the graph, either on your graphing calculator or on Desmos, you'd see something like this. Kind of a not so exciting graph. It's an even function, just FYI. By the way, does it pass the horizontal line test?
Yes.
Mm-hmm. No. Fails the horizontal line test. Passes the vertical line test, but not the horizontal line test. You get these 2 values here, and you start looking through and going, gee, you know, what in my list of possible rational roots is close to that? And then you focus in on 2/7, and you're like, okay, well, let's try 2/7. And let's see a decimal value for 2 divided by 7. So 2 divided by 7 there you go, about 286, and that's looking pretty good. So let's take a look at those a little bit closer. And because I have those possibilities, I'll start out with 2/7. You run through 2/7 and you get a 0. Yay. The lion and the lamb are best friends, and the Lions are going to win the Super Bowl. -2/7 is also a root. All right, so maybe it won't all happen. -2/7 is also a root, so that factors this polynomial down to this. That makes our life a little bit easier in terms of finishing this up. Now, I didn't bother like I did earlier to peel off the 49, which is the GCF from here, and then clean these up. I just said, all right, you know what? I know where this is 0, I know where this is 0. To figure out where this is 0, I'll set it equal to 0. Set it equal to 0 and solve using the square root property. Move that over, divide by 49. Don't overlook the fact that this becomes negative on the right-hand side, because that means when you take the square roots, and hopefully you remember plus or minus square root, you get plus or minus 2i. So altogether, those are your 4 roots. You can kind of tell that 2 of them are going to be complex. 2 of them are going to be non-real roots, because when you look at the graph, you only see it touching the x-axis at 2 places. But a degree 4 polynomial has to have 4 solutions. So where are the other solutions? Well, they have to be complex. So that's what's going on. Question?
Yeah, so every time it asks list all the possible rational roots, you include the I ones. Like,
No, those aren't rational roots.
Okay,
Yeah,
that's what.
yeah. So if I just want the possible rational roots, then that's that list that was on the first page.
This is for the next.
Yeah, so that would be all these numbers. These are the possible rational roots. Now, how come it didn't include 2i or -2i? Well, they're not rational roots, so that's why we didn't see those there. Okay, study hard. Good luck. If you have some questions, please reach out. Otherwise, see ya.